Assalamu alaikum. How are you, my dear students? Hope you will be in the best of health, wealth, and happiness. I welcome you all into my today lecture. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. Our today lecture is about the latent heat. It is unit number 7. The uh, title of the unit is Thermal Properties of Matter. The first topic is the latent heat, which is related to the change of state, the latent heat of fusion, then latent heat of vaporization, and then the evaporation. So let us start with the latent latent heat. Now, in the last lecture, I give a slight or a light introduction to the latent heat. I told you that it is that latent is derived from a Greek word which means hidden. That the heat, then it is related about to what? To the heat, hidden heat. So what does this really means? I'm coming to that point, but at that there I told you that latent heat is in fact the amount of heat energy required, the amount of the amount of heat energy, the amount of heat energy required, which can which can which can change the state of unit mass of a substance, the unit mass of a substance at its freezing point, at its melting point or boiling point. At its what? Mass of a substance at its melting point or boiling point. Melting point or boiling boiling point. That is called the latent heat. The latent heat, we have two kinds of latent heat. One we call the latent heat of fusion. The latent heat of fusion. What is the latent heat of fusion? It is the amount of heat energy required, the amount of heat energy required to change the state of unit mass to change the state of unit to change a unit mass of a substance, a unit mass of a substance from its solid states to liquid, from its solid state to its liquid state, at its melting point. At what? Its melting point. At what? At its melting point. Mathematically, this can be written as the latent heat of vaporization is denoted by H, the fusion by HF, and this is equal to the amount of heat energy required by unit mass of a substance, or this can be written as delta Q into HF into M. So let us start this with the experiment, and then I will be explaining it to you. Here, look, this latent heat, which I told you means hidden heat. What does this really means? I'm coming to that point. But this all required, this all is sorry, related to the change of state. What? It is related to what? To the change. It is related to the change of state. Change of state related to this. This change of say state from solid, from this is from solid from solid to liquid to then gases, gaseous state, and are in the reverse direction. Right here we only discussed from solid to liquid and then from liquid to gases. In order to explain this, let us consider some ice which we have taken here, and let we say that ice is usually that is the freezing point of water. Yeah, the ice temperature is usually at 0 degrees centigrade. For our experiment, we lower the temperature of the ice cube, and maybe if you would see your graph in the book, if I little remember from there, then it is, I think, starts from -20 or like that degrees centigrade. So its temperature is more lowered. We place these ice cube in a beaker as you see here right now. And now that is the beaker is placed here, then on the burner, right? After a while, we will just start the water heating. Here you see, look, let us see the graph. We will plot the graph between what? We will plot the graph between the temperature T in degree centigrade, and here the heat energy delta Q, but this is not there in the book. This is just, I want to add it from myself, and there is a reason to do this. And here is a time. Okay, so on the x-axis, I take two quantities. I take time also, and I take energy also. Now, let us suppose, for example, after every 1 or 2 minutes like that, as you see here, this is our time axis, right? And our heat energy axis also. Okay, so, and this is our what? This is the temperature axis. Now you see that, look, when you place the ice cubes in a beaker, the thermometer, we have the thermometer, and let's say the thermometer, for example, at the first place indicate a temperature of what? If it indicate a temperature of 20 degrees centigrade for us, sorry, -20 degrees centigrade. Now we place it on a burner, and we slowly start heating the ice cubes, right? Which temperature is at -20 degrees centigrade. I will just mark this as -20 degrees centigrade in this graph to make it matching to the one at your book. Now see here, look, as you add heat energy, what you are actually doing, you are adding the heat energy to the system. So when you add heat energy, You know that this increase the internal energy of the ice cube, and the temperature of the ice cube increases. Why? Because you know that the temperature is directly proportional to the amount of heat energy supplied. Increase in heat energy will increase the temperature. It will increase what? It will increase the temperature. And now that increase is indicated by the graph, and there is uniform increase, increase, increase. This happens until you the thermometer indicate you a temperature of 0 degrees centigrade here, right? Now a strange thing occurs. What happens that the thermometer reading will stay at 0 degrees centigrade despite the addition of further heat energy. As the time passes, there is no apparent increase in the temperature of the thermometer. Now, what happens at this point? Two things. Either this thing is wrong, that increase in temperature, increase in heat energy increases temperature, or there is some other explanation. But obviously, there is some other explanation. Why? Because experiment shows that increase in heat energy increases the temperature. So, what is the other sort of explanation? It is here. Now we are at the right position that this here, that is, this is called, as you know, that I just mark this. I told you in the beginning that there is a reason that I say increase in temperature. Now you see, look, during this portion, this amount of heat energy, this does not, this is delta Q, and this delta Q does not increase what? It does not increase the temperature. So if it does not increase the temperature, then what does it do? This energy is called the latent heat. Why it is called the latent heat? Because it does not increase the temperature, so it's hidden from us like that. So where does this heat energy goes? This heat energy goes in breaking the bonds between the ice molecule to change its state from solid to liquid, and this happens at a particular temperature, and that particular temperature is the freezing point of what? Water, right? They are the melting point of the ice cube. And you see, this is one of the reason that here I wrote that the latent heat of fusion, it is the amount of heat energy required to change a unit mass of a substance from its solid ice cube state to its liquid state. At what? At its melting point. So here you see that it is at its melting point. Now this purely depends, this factor, it is called the latent heat of fusion. The latent heat, the latent heat of fusion. In this latent heat of fusion purely depends on the nature of the substance. Different substances have different latent heat of fusion. Not all of the substances have the same latent heat of fusion. For example, in our case, this latent heat of fusion for ice equals, it equals to 3.36 into 10 raised to the power 5 joule per kilogram. If you convert 1 kilogram of ice into water, then you will need 3.36 into 10 raised to the power 5 joule of heat energy. Clear? For 1 kilogram. Now let us explain it more. So as long as there is a single ice cube, the temperature of the water will not rise. The entire heat energy added will rather utilized in converting the ice into the water. Clear? So there is no increase or rise in the temperature, and it will not be then indicated by the thermometer. Once all the ice cube melts, then you will see the rise or the increase in the in the temperature. So here you have the pure ice, here you have partial ice and partial water. Right now here what is going to happen? Here you see that there is what? That there is increase in the temperature until all of the water changes into what? Start boiling, sorry. So here this happens at a temperature 100 degrees centigrade. So here you have what? In this portion of the water, here you have all the water in the liquid form. Here you have partial ice and partial liquid, and it will continue until the water start boiling. Once the water start boiling, then there is no increase in the temperature, and it will be indicated by this constant graph. As you see, the time passes, but there is no increase in the temperature. There is what? There is no increase in the temperature. And this is called also the latent heat. Why? Because the amount of heat energy which you supply is not utilizing in increasing the temperature, rather it is utilized and breaking the bond between the water molecule to change its state from liquid to a gaseous state. So here in this region, you have what? Partial water, and partial what? And partial ice. Okay, and this, the thermometer will indicate 0 degrees centigrade until there is a single drop of water, right? So once all the water changes into steam, and you see that the steam is then they collected here, the wet steam. Now what happens here? That look, the temperature will then again start rising as indicated here. Okay, like this one, and then it will change into a plasma state like that. Few important point here. This heat is called the latent heat of fusion. Latent heat of fusion. And here you see, sorry, here this thing, it's is latent heat of vaporization. Latent heat of vaporization. Now I'm not going to write it. Why? Because it is as easy now as the previous one. The latent heat of what? That latent heat of vaporization. What it could be? It is the amount of heat energy required to change a unit mass of a substance from its liquid state to its gaseous state at its boiling point. This mathematically we can write that the latent heat of fusion is this, sorry, the latent heat of vaporization HF equals the amount of heat energy required per unit mass here, or we can say that this for fusion for and this for vaporization, this energy will be m into hv. Write better, you write mhf. Clear? So what does this indicates? Here this depends on what? On the nature of the liquid. What? On the nature of the liquid. and different liquids have different latent heat of fusion. Now, if you look to the graph here, if you see the graph, what happens? That definitely there is one interesting thing here, and that is the latent heat of vaporization, the latent heat of fusion, sorry, is less than the latent heat of vaporization. For example, the latent heat of vaporization, the HF for water is what? For the water, it is 2.26 into 10 raised to the power 6 joule per kilogram. So look, now if you calculate that almost for 1 kilogram of ice and for 1 kilogram of water, it is, what is that difference? How much is this difference? Let me just calculate it and within telling you that how many times it is greater, that we have one what, that let it is the 2.26 exponential what, 5, and then we have the sorry, not 5, it's 6, it's 6. So 2.26 into 10 raised to the power 6 divided by 3.36 exponential 5. And what is the answer? Almost 6.7. So this comes out to be 7. So you see that what does this mean? That the latent heat of vaporization in case of what? In case of the ice, that is the for ice, the heat of vaporization for ice, the for water, what I'm writing. This delta Q for water is 7 times greater than delta QF for water. This is 7 times greater. Okay, so 7 times more energy will be required. This is why if you place the ice cube in a cup and after some time when you just go and notice it is already changed into water. But if you did the same with the water, now it is changed into water, maybe probably you will wait for a day, right? So that it should be converted into what? Converted into heat energy, or you will heat it up to convert it into steam, right? Just placing it on the table would require a lot of time to get that energy. So this graph indicates here that latent heat of vaporization is greater than the latent heat of fusion. Reason: because more heat energy is required to separate the molecules of what the liquid, to change it into what, into a gaseous state rather than at their solid state. Okay, so converting into a gaseous state require more energy than changing from solid to liquid, because in the gaseous state the molecules are very far apart and you need more energy to supply to the liquid to just gain that state. And here in this graph you see it, this is solid, this is liquid, and this is the gaseous state. And these are what? These are the, this is the latent heat, this is the latent heat, but latent heat of fusion, and this is also a latent heat, and this is the latent heat of vaporization, right? So that is all about what? That is all about the uh, latent heat. Now the next process, the next topic is the evaporation. Evaporation. Now, what is evaporation? Evaporation, it is the process of what? Evaporation, it is the process, it is the process of changing liquid, of changing what? Of changing liquid into what? The liquid into the gaseous state, or the liquid into gas without at its melting point, without at its boiling point. Without its what? Boiling point. Class, remember, if I told here you is the melting point, so I was totally wrong. It is not the melting point, it is the boiling point. This happens at the boiling point, okay? Remember. I'm sorry for that. I don't remember whether I said melting or boiling, but if I did, that would be a big mistake, a blunder, I would like to say. So evaporation, there is a big difference between evaporation and the boiling. Here in the evaporation, that is evaporation is all-time continuous process, all-time continuous process, right? And this happens at all temperature, at all temperature, right? So that is the difference between the boiling and what? The boiling and the evaporation. Boiling can only occur at the boiling point. That is also the change of liquid into gaseous state, but that is at the boiling point, right? Boiling is that one. And while evaporation, it continue at all temperature, right? In the, if you see here, look, this is evaporation. In the evaporation, bubble cannot form since the vapor pressure is less than the atmospheric pressure here. But in the boiling, that is another difference, that the bubble can form and rise since the vapor pressure can overcome the atmospheric pressure, right? So that is the difference between the boiling and the evaporation. And one major difference I told, that evaporation continue at all temperature, while the continue at all temperature, and it is all time continuous process. One is this thing. Here you see the process of evaporation in this diagram. Look, that here as you see it. Now the next important point is, usually another important point is evaporation cause cooling. What? Evaporation cause cooling. And this is one of the system which is principle which is implied in the construction and design of the refrigerator, air condition, and all those appliances which cause cooling. The very simple example is that when you place, that is when you take bath with warm water and when you sit under the fan, right, you feel a cooling effect. It is why, because the evaporation causes cooling, because the hotter molecules quickly escape your body and leaving behind the cooler molecules and thus dropping the temperature of your body. So this is why evaporation causes cooling. That is there are factors on which the evaporation depends, factors affecting the evaporation. The first factor is what? The it depends on the nature of the liquid. Nature of what? Of the liquid. Different substances have different rate of evaporation. For example, the perfume, when you spray it on your palm, and in your other palm, if you take the same amount of water, then you will see that the perfume from your hand, or even if you use spirit, it quickly evaporate than the water droplet, right? And that is that shows that different liquid have different nature, and the rate of evaporation is different for them. And as I told here, if you just put some that spirit, or for example perfume that is easily available at your home, right? Spray some perfume on your palm and you see that they will quickly evaporate, and it will cause what? Cooling into your hand, right? You will feel cool on your palm. Why? Because the hotter molecule quickly escape into the surrounding, leaving behind the cooler molecules. So dropping the temperature of your body. Second, it depends on the area also, right? For example, when you wash clothes, right, This is very simple. You can do it at your home also. Look, for example, two pieces of the clothes, like for example, two shirts. One you fold the shirt, folded shirt, right? And the other you just spread it. So you see that the one which has a greater area, then the rate of evaporation will be what? The rate of evaporation will be greater. So large area increases the rate of evaporation. Why? Because look here, more molecules have the chance to escape the surface. Then when you fold it, so in the fold, less molecule have the chance to escape, right, into the surrounding. So this is one of the reason that increasing the area increases the rate of evaporation, right? The third one is the temperature also, the effect of temperature effect. That is, that greater the temperature, greater will be, faster will be the evaporation. Increase in what? Increase in temperature makes the rate of evaporation faster, faster evaporation, right? The molecule will quickly then escape. Here you see, look, if you have again two shirt, one you lay on a string outside in the sunshine, and the other you place in the room. So definitely the one which is in the sunshine, it will what? It will dry quickly. Why? Because the temperature outside is greater than the temperature inside. So increase in temperature increases what? Increases the rate of evaporation. The fourth one is the wind effect. Wind effect. Now, for example, the same this time, for example, if you take this shirt and let's say, for example, the shirt and this one, and if you place both, similar nature would be better. And if you place under one under the fan and the other just without fan in another room, then what will happen? The one under the fan will quickly dry. So why? It is because that the wind take out the hotter molecule into the surrounding very quickly than when there is no wind. So the wind also increases what? The wind increases the wind increases the process of what? The wind increases the process of evaporation. So that is how the effect is. So the nature of the liquid, the area, the temperature, and one is what? And the one is the wind effect, right? So mm, they are all the factors which can affect the process of evaporation. So this is our today lecture. Inshallah, in the next lecture, I will talk to you about the thermal expansion, that how the changes in temperature uh, changes the length or the volume of an object. So thank you very much. Inshallah, see you in the next lecture.